Okay, so let us start. Hope you guys can hear me. So let us start today's session. Um, so in this session, I'm going to cover what is known as regression analysis. This is the most important topic actually, regression analysis. Um, as I have already said, this is the most important topic in analytics. In fact, this is the bread and butter. So everywhere, anywhere in the world you would to work, you will use this technique big time. So it is important that you understand it clearly. In fact, this is the first step to any analytics technique that we always want to know the regression analysis before learning any higher complicated technique. And this technique is used in almost all types of all kinds of analytics, whether it's marketing, retail, finance, telecom, any type of analytics you will see, you will find the application of this technique. Okay. So now remember that in the first class itself, we talked about a couple of business problems that one will come across. For example, one will try to know if I provide discount on a product, say for example 5% discount, then what is the impact on my sales, right? That's one problem. One would think that okay, how does house price is related to the area of the house, right? Uh, or maybe one would think that okay, how can I classify my good customer and bad customer, right? So these are some of the business problems that one would come across in a in a company. Okay, so primarily we can classify the business problem, most of the business problem, into two groups. Okay, first group we call it as the problems of regression type, problem of regression. And the second type of problem, we call it as the problems of classification. So we'll try to understand in detail what is problem of regression and what is problem of classification. But the problem of regression is where we want to find out the impact of one variable on the other. For example, here we say that okay, if we provide discount of 5%, what will what is the corresponding impact on the sales? Okay, so how sales get affected, right? So the variable of interest is sales. So how changing discount rate changes the sales figure. So we want to see the impact of one variable, that is discount, on sales. So that is a regression problem, right? So what is a classification problem? Okay, so classification problem is where we want to classify, uh, you know, a data set into two different types or multiple types. Okay, the last business problem that we talked here. Okay, good customer and bad customer, right? So we have a pool of customer. We want to classify the pool of customer into two types: good customer and bad customer. So that's the classification problem. We classify customer into two different types. So that's classification. We'll see little in detail, like how to so first we'll go with the regression type of problem. Okay, so we will take a house price and area of house. Okay, so I'll plot. I have a data, so I have got price of house and the area. Okay, so this is the data I have. Okay, so if I want to buy a house uh, in Mumbai, I like to know that how price of house depend on area, right? So I have the information for say 50 to 60 houses in different parts of the city. So first price is say it's $50,000 within an area of 500 square feet. $60,000, 550 square feet. $70,000 with 600 square feet, 75, 650 square feet, 85, 750 square feet, and so on. Okay, so I have data points like that: house price and the corresponding area of the house. Okay, now let us plot this. Okay, now let us have something like this: 500, 550, 600, 650, 700, 750, 800, and so on. And then here we have 50, 55, 60, 70, 80, 90, 100,000. Okay. So in my y-axis, I have got price. I have got price, and my x-axis is area. Okay. So I'll just plot the data that I have with me. Okay. The first is 50, 500, right? 50 lakh, $50,000, and area is 500. So that will be this point. Sorry, this point. Then this point, and so on, right? You will see an increasing trend and point like that, right? Now this is how my points look like on a XYZ plane. Okay. Again repeating, X is area, Y is your price. Now what is the pattern that you can see here? Well, the pattern is that with increase in area, you see that the price is increasing, right? That is obvious, right? With increase in area, the price of house always goes up, right? But it's not purely, it's not in a proper manner. I mean, if you increase like houses from 500 to 550, the corresponding increase in price is like $10,000. But the same amount of increase in price with respect to the increase in area is not constant across the board, right? You will see sometimes it goes down, sometimes it goes out, right? So there is no perfect pattern. So we want to generalize that what is the relationship between price and area, or in other words, I would like to know a few things here. First, relationship between price and area. So that's first question I have. So second question I want to know, in that given area of house, I want to predict price of the house. Okay. And yeah, so that these are the two things I would like to know. Okay. So how am I going to do that? I'm going to do that by doing what is known as regression analysis. So that's where I'll be using regression analysis. So what is regression analysis? Well, we will not go into the details of mathematics here. You can watch my videos on regression analysis, wherein I covered the mathematics of regression analysis in detail. So we will just see the application of regression analysis, and we will cover them as theory part as you know as much less as possible, because it's not going to help much. There are a lot of complicated mathematics involved here. Okay. So in regression analysis, what we try to do is that we try to generalize the trend or generalize the pattern in the data. Okay. So what we do is that we try to you know, plot a line inside the data points that passes through the middle of the data points, right? Now, you must be wondering that how we can plot, how we can draw a line, okay, on what basis? How do we ensure that it passes through the middle of the data points? And what is the purpose of doing this? Well, as you know that in the last class I spoke about the linear equations, right? Y is equal to mx plus c, right? So every linear line or every straight line has can be written in the form of y is equal to mx plus c, where c is the constant or the intercept and m is the slope, right? So we will try to know that can we have this relationship between price and area in a linear equation form, where y will be my price and x will be my area. So if you know the relationship between price of house and area in a y equal to mx plus c form, we can find out price given area, right? Because this is an equation. All you need to know that the slope and the intercept, right? For that we want to draw a straight line that passes through this line, passes through the data points, right? Because that generalizes the trend in the data, right? That makes sense because there will be sort of error also, because see, you will find that not all points are lying on the straight line. So these are the certain points. For example, this is one point which lies above the line, right? This is one point which lies below the line. Okay, so there will be error. One will be negative error, there will be positive error. Okay, but still, this line is able to generalize the pattern or generalize the relationship between price and area. So that's what we essentially do in regression analysis. Okay. So how we draw the line, how to make sure that the line passes through the middle of the data points, we will see that. Okay. So for that we will use a technique known as OLS, or ordinary least square technique. Okay. So let us learn how we can do an OLS regression. So we'll use OLS to find out the slope and intercept. Okay, I'll draw it again. So something like this, right? Regression looks like something like this. So this is price, this is area. Okay. Now, how to find it out? How to ensure that the regression line passes through all the data points at the center of that's the best regression line. See, we can actually have a line like this, a line like this, but which line is the best line that fits the data? This line, right? You will agree with me. This line doesn't fit the data properly. This line also isn't the fit the data, but this the first one that I draw fits the data properly, right? And why is it so? And how to make sure that, right? We don't do it manually, we do it algorithmically. Okay, so how do we do it? Okay, so if I draw a regression like this and I have both the data points, okay, what happens is that I get error, right? If I find a house here, right, this regression line passes through here, so my equations, my regression equation or my regression line say that if my area is, say for example, x1, my price will be xy1 here, but I see the actual price is this one, the data points, the crossbar, right? So by actual price is actually y2, which is different, which is more than y1, right? So I call this portion as the error. Okay, so y2 minus y1 is my error, right? And this is a positive error, right? Take this point, okay, take this point, okay. The house price predicted by the regression line is this one, this point, but the actual price is this point. So what is the error? This is the error, right? That this is the error. Okay, so we can, that's a negative error because the data point is lying below the regression line, right? So that's the negative error. Now what we do is that we square all these error. So for all data points we have some error, right? It could be 0, it could be positive, it could be negative, right? So we'll have error 1 and we take this square, and I'll say why we are squaring it, okay? Then we take error 2 and we square it again. Error 3, square it again, and then keep on adding, okay? And up to n observations. If you have like n number of observations, we do that, okay? And what we do that this is called sum of the error, okay? Or in short form we can write it as this, like this: I is equal to 1 to n square, okay? We call it as sum of the errors, right? Sum of square of errors, okay? So how we can find out error? Well, error terms can be given by like this, right? So every linear equation or this line can be formed like this: y is equal to a plus bx plus error, right? If I am wrong, am I right? Y plus a plus bx plus error, right? So if you put the error, positive error or negative error, you will get the exact house numbers, right? But this error is could be positive, negative, or could be 0. When the data point line on the regression line, the error is 0, right? So how do we find the error? So error is nothing but y minus a plus bx. Or in more technical form, in statistics, we actually write it in such a manner. We call it beta 0. So a is known as, so intercept is known as beta 0, and the slope is known as beta 1. Okay, this is more technical. Okay, this is just a notation. So error is y minus beta naught plus beta 1 x. Right? So for every data points, we'll have error 1, error 2, error 2. Right? So you put it in this equation. Okay. The sum of error equation, you just put it over there. So what do you get? Y is equal to n. So our error is this one, right? So yn minus beta 0 plus beta 1 xn, and you just square it. Okay, I'll repeat for you guys if you do not hear properly. No problem. I'll just repeat. So till what point were you able to hear? Can you just
square till error square, sum of error square.
Yeah, what the significance of the equation? I'll talk about it. Don't worry. Okay. So you could understand till sum of error square, right? I wanted the sum of error square, right? So till this point you knew, right? E1 square plus E2 square plus E3 square and all that. Okay. So now I wanted to know that how do we compute the error? Okay. How do we calculate error? I said that every data point can be expressed in this form: y equal to a plus bx plus error, right? Because if you add the error, you will get the actual house price, right? Y is equal to a plus bx is just the line. But if you add the error point, so error is what the difference between the line and the actual data points. Okay, if you add it, then you will do the adjustment, right? So error is given by y minus a plus bx. I just took a plus bx to the right hand side. Okay, I hope you are okay with this equation, right? I'm just skipping the step. So error is nothing but y minus a plus bx. technically we actually write y minus beta naught plus beta 1x. So beta 1 is the intercept, we call it intercept, and beta naught, and beta 1 is the slope coefficient. Now our intention is to find out beta naught and beta 1x. Okay. So now this is error. So we put this in the sum of errors equation. Okay. So sum of error equations becomes yn minus beta 0 plus beta 1 xn whole square. Right? Is this clear now? And this is generalizing actually. This is just sum of, right? Can you repeat the question, Pawan? Anyway, so yeah. So now question is, see, our intention or the objective of this analysis or the ordinary least square analysis, OLS analysis, is to find out what is beta naught and beta 1. If you know beta naught and beta 1, you will be able to find out the relationship between y and x. Okay.
Can OLS ordinal these?
Yeah, we will try to find it out, Pavan. As is in any linear equation, this is the intercept, and this is the slope, right? And we still don't know about it. Okay, this is a theory. Okay, we will learn how to find it out. Okay, mathematically. Okay, so that's the way we will do. Okay, but as you know, in any linear equation, we have the intercept and slope, right? In diagram you can see. Okay, so, and we will see how we can find it out using the data. Okay. Now we have sum of the errors, square sum of the error. Okay, is equal to yi minus beta naught plus beta 1 xi all square, right? Y is equal to 1 to n. Hope it is clear, right? Now this is the sum of the errors. Now the condition in OLS, OLS stand for ordinary least square. Okay, so this sum of the error square is also known as cost function. Okay, we also call it as cost function. So the intention here is that, and we also call it a least square, right? The word least square means, so what does that mean? Well, it means that we will try to have a regression line where the sum of the square is minimum, or the error sum of the square is minimum. That is the best regression line that fits our data set, or the cost function is minimum. Makes sense, right? Because we want the regression line to pass to the middle of all the data points, right? So for that to happen, the error, the sum of the error, if you add all the error, it should be as minimum as possible, or the most, or the least error has to be there, or the minimum error has to be there, right? So that should be the condition. That's why it's known as ordinary least square. That means it has to be least. Okay, so so that's the way. That's the only condition. And how does that condition help us finding out beta naught and beta 1? It actually helps us out a lot. Okay, so how? Oh my God! So you are not aware of what is SSE? SSE is sum of square of error. Okay, so that's the way it is. Now what we will do is that we will try to find out what is beta naught and what is beta 1. Okay, that's the most important thing. Now find, how can we do that? Now the condition here is that the SAC or the cost function has to be minimum, right? So what we will do is that we will and how do we ensure that it is minimum? We use derivative for that. Okay, so we use derivative for that. So for example, there is a function here. Okay, there is a function here. So how do we know that this function is how do we minimize this? Well, we take the first derivative with respect to s and make it 0, back derivative with respect to y and make it 0, and we find out the data points where exactly this is becomes 0, and we take second derivative and see if it is less than 0 or not, right? If it is less than 0, then that's a maximum point. If it is less than greater than 0, we call it as minimum. So this is from the calculus. Okay, don't worry if you are not sure about the calculus. If you have forgotten calculus, don't worry about it. This is not going to be used in a great detail, and as I said, I will not be covering it in a great detail. So the mathematics part I have covered in detail in my video, so you can just watch it and if you really like to learn. But it's as I have said, this doesn't really matter because the algorithm in the software takes care of all the calculations, initial calculations. But it's good to understand it. Okay. So now let us learn how the OLS estimate happens. What we do in OLS estimate is that we try to minimize the sum of the square, error sum of the square. Okay. With respect to what? Beta naught and with respect to beta 1. Is there a question? Okay, let me let them write the questions before that. Yeah. So no, you guys don't need to any study any formula here. As I have said, most of the things are covered in the videos. So you can watch these videos and learn the theory part. So don't worry about. I know when I introduce the regression analysis for the first time, people get scared a bit because there is a little more mathematics that is involved here. So there is a sense of feeling that you are going back to school and learning things, everything all over again. But that's not the thing actually. Okay, it will be more interesting when we use software to do it. Okay, when we see an example or an assignment, we'll get to know about it. Okay, so don't worry about it. Okay, I'll so if there is something is not clear, I'll cover it or I'll just teach it again. So we take first derivative, we equate with 0 and find out the beta coefficients. Okay, so how do it is something that is covered in detail in my videos. Okay, so it is very simple. For example, say you want say y is equal to a plus sorry 2 minus 5x square, right? So I want to know what is the minimum value of this function, right? So this is a function. So df by dx. So at what value of x this function attains a minimum value, right? So if I take first derivative, this becomes 0. Then this becomes 10x. Plus this becomes 3. So I equate it to 0. And x is equal to 3 by 10. So at x is equal to 3 by 10, my function attains either maximum or minimum. Okay. If I take another derivative of this function, okay, d square f by dx square. So what I get? Only minus 10. So this is less than 0. Hence, I conclude that at x is equal to 3 by 10, I get minimum value, or the function attains minimum value, right? So in other words, let me do it graphically, okay? So the first observation, the error is here. The next observation, the error is here. The next observation, error is here, okay? So you can see the error points are like this, okay? Oh, this is wrong actually, this is wrong, okay? Go to the next one. Okay, so you will see the error in the cost function, something like this, okay? So here I have beta naught, here I have beta naught. So you just put randomly the beta 1 and beta naught and check what is the error sum of square, I'm saying, okay? So the error sum of square is at this level, when beta naught is this one and beta 1 is this one, is this. Similarly for this, okay? Now I have got the error something like this. So where exactly it is actually minimum. So this is where it is attaining minimum, okay? This is. So these two data points where we have the x-axis and y-axis intersection, we will choose, say this is one. So these two data points are going to be the final intercept and the slope coefficients for our regression line. Okay, so that's the way we compute. You can do it both mathematically. First, for example, when we like take the first derivative, take the second derivative, and do it, or you can do it manually also. That will be less efficient. It requires a lot of computational method where you just randomly put beta 1 and beta naught and find out the sum of the error square and plot it and see where exactly it is coming minimum. Okay. But how it's very difficult to do actually, because they're just you cannot just try it randomly any number, right? So it's a bit difficult, but you still can do it with simulations. Okay, now yeah. So Vivek, that example that I gave is actually just to show you that how to find minimum value of a function. Okay, so x doesn't come here, so don't confuse with x. Okay, we are only worried about beta naught and beta naught. So our derivative is coming with respect to beta naught and beta naught. So we need to know where the beta naught and beta 1 are in this line. Okay, so we are doing it with respect to beta naught and beta 1. So beta naught is in x-axis and beta 1 is my y-axis, and I plot the sum of the error square in the xyz plane. So and I found that at one place I have the minimum number. Okay, that's about ordinary least square estimation. We call this as estimation. Okay, we estimate to find out what it is. So for the housing example that I gave, say for example, I'm giving it as an example. It could be different also. Say house price is equal to say 45,000 plus 0.5 into area. So this is our the regression line. Okay, so 45 is the intercept, 0.5 is the slope. And this is just an example. Okay, I haven't estimated it. Okay, just for sake of example, this is how the regression line looks like. Now, if somebody says that the house that I am going to purchase is 1,000 square feet, so what could be my price? So what is the price? 45 plus 0.5 into 1,000, right? So that is, it should be 0.5. Okay. Okay. So 45 plus 5, 0.8. That will be great. So plus 8, something like 53. Okay. Something like that. Okay, so house price it's not coming accurate as such, but yeah, you will get 53 as the final price. So now given area, you'll be able to find out what is my house price, right? And second thing that you will get to know is that how is house price related with area. it's related positively because the coefficient or the slope coefficient is positive, right? That's why it's positive related. That means when house price, the area goes up, the house price also goes up. So that's another interesting pattern. By how much, if you increase area by 1 square feet, how much the house price goes up? It is goes up by 0.08 thousand dollars. Okay, because this is in thousand. Okay, so if you increase area by 1 unit, the corresponding unit in increase in house price is going to be 0.0. So how is that? Because that is the slope. Okay, so that's the way we yeah. So now the two questions that we took up in the beginning is now very clear, right? That we now able to find out what is the house price given area, and we also now able to find out the relationship between area and house price. So if you increase area, how is going to house price affected? Will it increase? Will it decrease? By how much will it increase? So all these questions can be answered by looking at the regression equation. Don't worry about it. That if the mathematics is not very clear, we will see it in the recorded videos. It will be much more clear there. And when we do it in SAS, it's not going to be that tough. Because the algorithm takes care of all the optimizations or the derivative that happens. It's taken care of inside. The next problem that we actually talked about is the classification problem. We classify customer into different types. Okay. Now that I'll cover it in a separate session after this one. Let me show it to you first how we do it in SAS, and after that, and we will see the classification. Okay. So I'll take a 4-5 minutes break. Okay, and then we'll start again. Okay.